Hi everyone, it is pretty late at night again, but today I'll talk about diffusion models. Diffusion models is very beautiful in terms of the mathematical theories behind it, but there are so many resources written about it online, and it is very hard to connect all the theories and beautiful things together. So today I will try to do it. I've been wanting to do this topic on diffusion models for quite a while, but because of the vast amount of information, I could only get to it now. So diffusion models, probably everyone has heard about it in terms of image generation because it is the model that is powering all the image generation tools that we have nowadays. The way that I view diffusion models is that we can regard the diffusion model as a model that maps a probability distribution to a probability distribution. So I'll just write that down, a model that maps a probability distribution to a probability distribution. And I'll explain how this sentence actually ties into image generation, right? So let us just consider the problem of image generation. So in image generation, let's say someone gives you 10 million images and asks you to generate a new image. These 10 million images are real world images, right? The things that we see in real world are pretty much well defined. For example, like it is possible that I'll see a cat or a dog in real life, right? But it is much more unlikely that I will see something like a broken television screen, for example, which if you sample the pixels randomly, you'll probably get a broken television screen. So the problem is as such, someone comes and give you a data set, right? Let's just consider like real world images. So n is a very large number, xi or let's say 32 by 32 pixel images. You can imagine my eye, right, as a 32 by 32 pixel camera. And every few seconds, it will take a snapshot of what I see in front of me, and that would contribute to one sample in your data set. And we want to generate an image, let's say x hat, such that x hat is not in the sample, right? It doesn't make sense if you just give me an image that I've seen before. I want a new image that resembles something that I might be able to see in real life. For example, if the images that I see are all images of pandas, then I would expect you to generate a picture of a panda in, let's say, another position, maybe sitting on top of a tree that I have not seen before. We don't want you to just take an image from the dataset that I give you and give it back to me. In particular, we want a new image. And here is where the mapping distribution to distribution comes into play, right? So as I've said, let's consider the distribution of real-world images, right? The space is precisely the 32 by 32 pixel images. And among this space, there are some points that are more likely to be what I can see in real life than others. For example, an image of a cat is something that I will see in real life, but an image of a broken television screen, which is what happens if you sample all the pixels randomly, it's not likely to be something that I will see in real life because I'm not going to stare at a broken television screen. If we plot out the distribution, obviously I'm just going to draw some very wiggly lines. The probability density of each region of this R32 by 32 space is going to be very different. So for example, you can think about all the cats being clustered at this peak because cats are likely something that I'll see in real life. Let's say maybe pandas are over here. And then like something like a broken television screen would probably lie at a minima over here. Right, so this is a probability distribution over R32 by 32. What we want to do is using this data set, we want to construct some form of distribution so that we can sample from it. But this turns out to be a very difficult problem. You have to construct something over the space of R32 by 32 with just n set of data points. So how do you do that? This is the idea of diffusion model, or the idea of mapping a distribution to a distribution. So this is the distribution of real-world images, which is a very complex distribution. Let's consider a easier distribution, which is the multivariate Gaussian distribution. So the multivariate Gaussian distribution is a much simpler distribution. 1D Gaussian distribution looks something like this. So for each of the 32 by 32, which is 1024 pixels, we just sample from this 1D distribution independently at random. And that would be our 32 by 32 image. And if you actually do that, what you'll get is exactly something like a broken television screen, right? It will just be a speckle of white, black, pink, all the random pixels mashed up together. It will not be something that you will see in the real world, but it is very easy to sample from. So this is the multivariate Gaussian distribution. I will just write that the space is also over R32 by 32, and we just basically sample from a normal 0, I32 by 32. So note that I32 by 32 I'm using over here to denote a identity matrix that is of dimension 1024 by 1024. And when we sample from it, we are actually getting a vector of length 1024, and that can be just rearranged into a 32 by 32 pixel image. I hope that makes sense. And diffusion model is really the transformation between these two distributions. So diffusion model allows us to transform from one distribution to another, and therefore it maps a probability distribution to a probability distribution. So I will write M as the model and I'll write theta because later we'll notice that it's a parametrized model. So it is going to be a deep neural network model and it's going to have some weights, and the weights are the parameters of the model. I just want to clarify over here that I am sort of overloading this term of map. What I have said over here is that one, I've said that diffusion models map a probability distribution to a probability distribution. But I'll overload this term map in the sense that in reality, diffusion models map a sample from one probability distribution to a sample in another probability distribution. And these two statements are not contradictory, right? That's why I'm using the word overload over here. So in reality, this m theta is a model that will map, in our case, our R32 by 32 real-world image into R32 by 32 multivariate Gaussian distribution, or vice versa, right? It is going to map a sample from one probability distribution to a sample in another probability distribution. And in doing so, it is actually mapping a probability distribution to a probability distribution. You can just imagine, right? We can sample n data points from one probability distribution, pass them through the model, and these n data points should build up some sort of empirical distribution in the probability distribution that is mapped to. So it is also mapping a probability distribution to a probability distribution. I just want to clarify this because this is really the operational form of the model. And when I say it maps a probability distribution to a probability distribution, that is conceptually what is happening. Okay, nice. Okay, so now let's move on to the diffusion model process. So how does the diffusion model actually achieve mapping a probability distribution to another probability distribution? This is the way that I learned in my university, so I'll begin with that now, and I'll introduce like all the various connecting ideas later. So what I've learned is that we can view diffusion models as a Markov chain. Markov chain has a lot of states. We can think of it as having T states. And each of these states only has arrows going in and out from adjacent nodes. In our case, each of these states xi is a R32 by 32 vector. And here T refers to the time step. So that is why it is useful to think of it as a Markov chain for now. So there are T plus 1 nodes over here. The starting node is x0, and we want the x0 end of the node to represent one distribution, or maybe let's say the source distribution, right? So in our case, this will be the real world image. And we want xt to represent the target distribution or the other distribution that we want. So in our case, this should hopefully be something like a Gaussian distribution. And the diffusion model is really the arrows in between this set of nodes. So to discuss about the model, we just have to talk about these arrows, right? There are two parts to a diffusion model. One part is the forward diffusion process. And just to make sure we get the terminologies correct, so this forward is really referring to forward in time. If we look at this chain as a discrete time Markov chain, right? Forward in time means the index will increase with time. So it goes from 0 to t. In the forward diffusion process, what are we doing? We are getting something in our source distribution that is a real world image, and we want to get a Gaussian distribution at the end. And this is sort of corrupting the image, right? We are given a very nice image and we just want to convert it to noise. It turns out that this forward diffusion process is very easy because we just need to inject noise into the image to destroy the signal. And we want to do this incrementally, right? We want to do it across t time step. We don't have to just inject noise at one go. We want to slowly corrupt the image across the t time steps. And what people have done, and I think this is a pretty straightforward idea, is to have a variance schedule, a collection of parameters beta t from t equal to 1 to t, with beta t being some value between 0 to 1, such that we can define the next state xt as square root 1 minus beta t xt minus 1, so some multiplier times the previous state plus square root beta t times a noise, normal 0i. Just to make it clear, at the x0 end, we have a proper image. We want to slowly degrade it as time passes. Xt minus 1 is a clearer image. We multiply it by a coefficient that is less than 1. So the signal is really being degraded, right? Signal is degraded since square root 1 minus beta t is less than 1, less or equal to 1, and we are injecting some noise, right? We are injecting noise. And this equation really describes one step in the forward diffusion process. And we can just leave it like that. But I feel like that will be doing us a huge disadvantage later on, because to understand the backward diffusion process, we really need to understand the forward diffusion process really well. And there are also a lot of niceness to this way of formulating the forward diffusion process. So if you don't mind, I'll just talk more about it. One thing I want to point out that is not very obvious is that there is an invariance, which means something is not changing. Let me just put an exclamation point. There is an invariant, and the invariant is that if the variance of x0 is equal to I, right, we can always ensure this by scaling our data set. Then the variance of xt will be equal to I for all t in 1 to capital T. So what this means is that if we can control the variance of the initial state, we can ensure that the variance of all the intermediate states in our diffusion process will be constant, which is very nice for training. To prove, we can just use the definition of xt in the one-step forward diffusion process to get the variance of xt is the variance of substituting in the definition. These two terms are independent of each other because for the noise, we are just injecting it independently of the state anyways. And we know that the variance of a constant times a random variable is the constant squared times the variance of the random variable. So this is just 1 minus beta t times the variance of xt minus 1 plus beta t times I. And by induction hypothesis, variance of xt minus 1 is I. So this is just equal to I. And we are done. Just to repeat what I've said, if we can control the variance of our input, all the intermediate states should have relatively constant variance by theory. And this is also a very good mathematical trick, as I'll show later on. Another thing that I want to note here is that there's a very nice reason why we are using the Gaussian distribution as the target distribution, or the distribution at the other end of the chain. The thing that I want to point out here is that the Gaussian distribution is a probability distribution with the highest entropy subject to a variance constraint. So I think this is not very difficult to prove, so I'll just attempt to do it now. In math, right, what I'm saying is the normal distribution or the Gaussian distribution is precisely the argmax over all the probability distribution. So P is a probability distribution. It is the probability distribution that gives the highest entropy. If you sample X from P, the highest entropy subject to the variance of X sampling X from P being equal to I. So I'll try to do this in 1D. In 1D, I claim that the normal distribution, which is something that is shaped like this, is the distribution that maximizes the entropy subject to a variance constraint. So in 1D, I think firstly, we should make an observation. So without loss of generality, we can assume the probability distribution P is centered at 0. So in other words, the expectation of x where x is sampled from P should be equal to 0. And this is really because the entropy and the variance do not care about the center of the distribution. You can translate your probability distribution and the variance will be the same. The entropy is also the same because the entropy is a function of the probability density at each part, irrespective of its location. So we can just assume that the distribution is centered at 0. And when tackling an optimization problem, I like to write out the objective and constraints in a way that I understand. So in this problem, we're trying to maximize over a probability distribution in 1D. So the density at each point, we like to maximize the entropy. So what is entropy? So entropy is the expectation of log 1 over px. And in integral form, it is the integral over r log 1 over px weighted by the probability density itself, dx. Let me just convert it to a minimization problem. So log 1 over px is really minus log px. Since we are maximizing a negative quantity, we should be minimizing the integral of log px times px dx. This is subject to, firstly, P must be a valid probability distribution, and to encode that, it's really saying the integral of Px dx must be equal to 1, and the other constraint is that the variance must be equal to, let's say, C, right? Variance is constrained, so let's say the variance is C, where C is something that we know. So the variance is x squared Px dx. So subject to the variance is equal to C. So note that normally it's x minus mu, where mu is the mean, but we have already assumed that all distributions that we're considering have 0 as their center. So that's why I can write it like that. And whenever we have an optimization problem, I think one of the go-to method is to use the Lagrangian. So we can formulate this optimization problem as a Lagrangian with dual variables lambda and mu, where the Lagrangian is the objective itself. So let me write px in front minus each of these constraints. So lambda times px dx minus 1 minus mu x squared px dx minus c. And we know that at optimum, this Lagrangian must be stationary with respect to the optimization parameters. In particular, because we're optimizing over the probability distributions, it must be stationary with respect to all of these px, right? The Lagrangian basically makes this constraint optimization problem an unconstrained one. So we can just immediately take the derivative at each of these optimization parameters. The partial derivative of the Lagrangian with respect to one of the optimization parameters, so let's just say px, right, is equal to, we can just differentiate into this integral, and this will be equal to log px plus 1 minus lambda minus mu x squared. And this should be equal to 0. So this is really saying that log of px should be equal to lambda minus 1 plus mu x squared. And this must hold for all x because this partial derivative should be 0 for any optimization parameter, so any px. And what this is really saying is that px should be proportional to e to the power of mu x squared for all x. Lambda is a dual variable over here. And if you take the exponent, e to the power of lambda minus 1 really takes on the role of a normalization variable to make sure that the probability distribution is normalized, integrates out to 1. The upshot here is that px is proportional to e to the power of mu x squared. And the only distribution with this property is the Gaussian distribution, right? In particular, this mu must be negative because it doesn't make sense for the probability density to explode at the tail. That will never integrate out to 1. So let me just write. So the upshot here is that the probability distribution that maximizes the entropy is the Gaussian probability distribution. And just to make sure that I show this, so a normal 0 sigma squared Gaussian random variable would have a probability density 1 over square root 2 pi sigma e to the power of minus x squared over 2 sigma squared. So you see this e to the power of minus x squared over 2 sigma squared. That is precisely this term, right? Where mu, here mu must be negative for it to be a valid probability distribution. This is really a property of the Gaussian distribution. And why is this a very nice thing for us? So Let me just copy a diagram from earlier. The point was, why is this very nice for us? Well, on one hand, we have the probability of real-world images, right? So this looks like some very hard to model distribution. On the other hand, we have a distribution that has the maximum entropy. And by our definition of the forward process, we know that all the intermediate states must have a constraint variance. So on one hand, we have the distribution that we want to model. On the other hand, we have the distribution that has the maximum entropy. This is exactly like in statistical physics, right? So when I think about diffusion, what I normally think about is I am in a room, and let's say the room has an air freshener, right? This air freshener will spray out some particles to make the air fresh. Initially the particles will be concentrated in the space around the air freshener, but after a while it will diffuse out. And in doing so, the entropy actually increases because there's just more configuration of air freshener particles mixed with the rest of the room particles than if they are concentrated at a particular spot. This is exactly what the diffusion model over here resembles, right? At each stage, we are injecting noise into whatever sample from this probability distribution. On the other hand, we have a state or a probability distribution with the maximum entropy that is allowed by the system. And the system has a variance constraint. So the Gaussian distribution, on the other hand, has the maximum entropy. So I think this is really, really very nice, and diffusion model is aptly named in this way. The other train of thought is that if we want to model a particular distribution, we should use the most general form of distribution to approach it. Given that we don't know how to specify the distribution of real-world images, why not start out with the one with the highest entropy as the universal starting point to approach a distribution that we don't know about? So this is exactly why the distribution on one end of the chain is the Gaussian distribution. I hope all of this makes sense because from a physics perspective, there's a lot of intuition to be gained just by the forward diffusion process equation. Let me just put one more thing over here. So I just want to highlight a third point because this will make our life very easy later. We know the one-step forward diffusion process, which is xt is equal to square root 1 minus beta t, xt minus 1 plus square root beta t, a noise term, right? This is all good for a one-step process, but what if we want to take, let's say, n steps, or what if we want to know xt from x0, for example? Firstly, note that this is a linear recurrence, so it should be pretty straightforward to know xt from x0, right? At every step, we are just multiplying the previous state by a multiplier, and then we inject some noise. If we want to express xt in terms of x0, we know that the multiplier should be the product of all the multipliers along the way. So what is the product of all the multipliers? It's just 1 minus beta t, 1 minus beta t minus 1, dot, 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 1 minus beta 1, x0 plus some noise, right? If we add up a lot of independent random noise, it's still going to be a Gaussian random noise. And what is the coefficient over here? Well, we can use the invariance just now to imply out this coefficient. Just for clarity of notation, I'm going to denote alpha t bar as the product from 1 minus beta 1 all the way to 1 minus beta t. So this term over here is going to be square root alpha t bar. We can write xt as square root alpha t bar x0 plus square root 1 minus alpha t bar, random noise. And the reason why I got square root 1 minus alpha t bar so easily is because the variance of xt must be equal to I. If we assume the variance of x0 is equal to I, this coefficient, by Pythagoras theorem, it must be the square root of 1 minus the previous coefficient squared. And that is how we get the n-step forward diffusion process. And this will help us a lot later on when we are deriving the backward diffusion process. So let me just write it over here and box it up. So one last thing that I want to point out over here is that I want to talk a bit about this variance schedule. Whenever we get an equation, we should try to get some intuition from it. So what is the intuition over here? Well, xt is the product of square root 1 minus beta t. Let me just go back to this diagram. On one hand, we have the real world image. On the other hand, we have a noisy distribution. We are injecting noise at each step of the way of the forward process. And the goal is that by the end of this t time step, we want to completely or almost completely erode the image. And what does that mean for the variance schedule beta t? Well, there are two things that we want to achieve, right? So for beta t, so one, we want square root 1 minus beta t to be pretty close to 1. And the reason is because in a single step, we don't want to erode the image too quickly, right? In the backward process, we need to reconstruct the signal in some way. And if we just inject too much noise in the forward step, it's going to make the backward process very difficult. So we want square root 1 minus beta t to be very close to 1. And in other words, this beta t should be something that is small, like something like 10 to the power of minus 2 or 10 to the power of minus 4. And the other principle is that by this n-step equation, we want to completely erode the image at the end of t time steps. And we know that xt is equal to square root 1 minus beta t multiplied by 1 minus beta 1 x0 plus the corresponding coefficient of some noise. So we want this combined multiplier to be something that is very close to 0. And this will symbolize that we have completely eroded the image. So we want 1 minus beta t, 1 minus beta 1. So these are the two considerations for choosing a variance schedule. We want each of the individual variance schedule parameters to be very small, but we want that across the t time steps, the product of all of them should go to 0. This affects our choice of t as well as the variance schedule. And that's all I want to talk about for the forward diffusion process. Let me just copy over the diagram from earlier. So we have understood the forward diffusion process as injecting noise, right? This is just injecting noise. And one of the key equation is we can write the next state as a multiplier times the previous state that corrodes it, and we inject some noise. And now for the backward diffusion process, which is going to be a bit more involved. So just to mention again, in the forward diffusion process, we want to map the distribution of real-world images to the Gaussian probability distribution. And that is easy because we can just inject noise at each step. But in the backward diffusion process, what we are starting out with is the Gaussian distribution, and we want to get out the real-world probability distribution. And that is going to be a more difficult task. So now we'll talk about the backward diffusion process. So again, this backward is really backward with respect to time, right? With respect to time. So we are going from t to t minus 1 to t minus 2 all the way back to 0. And the mental model that we should have is given xt, how do we get xt minus 1, which is supposedly a clearer image? Suppose that I pass you an image xt. What would you want to know? You would want to know which are the possible xt minus 1s and which one of them would likely give you as the result if you inject some noise into each of them. It is no longer about injecting noise into yourself. You must know what are the possible initial states. For example, if I show you a blurry picture of a panda, you don't know what the panda is doing, but you would want to make a guess about what is the panda possibly doing. Like, is the panda possibly sleeping? Is the panda possibly eating? And which of them, after you inject some noise, would give you the blurry image that you have received now? Of course, that is a lot of English, and it is always better to write it out in some mathematically understandable way. Given xt, can I know the probability distribution of xt minus 1? Because if I can know this, I would just try to go in the direction of the state xt minus 1 with the highest probability density. But knowing this is pretty hard. If there's any lesson that we have learned from the forward diffusion process, it is if we know any previous state, we'll be able to get the probability distribution of all the states at the back relatively easily, right? We just multiply some factor and add more noise. So in this case, why not condition on x0, since x0 is the most previous state, right? So let me just write it out and I will give more motivation later on. To condition on x0, we just write it out. We just write out the definition of conditional probability, right? So we integrate over x0. x0 lives in the space of R32 by 32. We integrate the conditional probability density xt and x0, p x0. So the conditional probability equation is really saying if we want to get xt minus 1 given xt, we consider all the possible x0 and we consider what's the probability of getting that particular x0 given xt, and then we can condition on both xt and x0 at the same time. So we'll get something like this. So now we have two terms, right? This term is actually easy to get. And this seems like an even harder problem to solve, right? Because previously, the problem that we have is given xt, how do we predict the immediate previous state, which is xt minus 1? Now this is saying, given xt, you need to predict x0, which is a state that is much further in the past. But it turns out over here, solving the harder problem is actually good for us, and we will head in that direction. So instead of solving this problem, why don't we solve these two problems? Given xt, how do we get x0? And then if we can solve this problem, given xt and x0, how do we get xt minus 1? Like sometimes when I look at these two problems, it reminds me a lot about life philosophies because this is very reminiscent of how humans behave. We are all at some particular state in our life and we don't really know what is the next step to take. So a common methodology is you ask yourself, where would you want to be in 5 years or 10 years time? And that is your x0, right? You're at xt now and you don't know xt minus 1. But you will probably have some idea of where you want to be. Based on that, you try to imply out what is the next step you should take. That is how humans typically structure their life trajectory and stuff. In this case, this is exactly the same. We are at some stage in our diffusion process and we want to know our previous state, but it is pretty hard to know that. So instead, we ask ourselves, given our current state, can we predict what our end result will look like? And our end result is the x0. And based on that x0, let's take an incremental step towards our goal. So our prediction of x0 might not be the final x0 that we achieve, which is similar in life. Like in life, you have your 5-year or 10-year plan, but you might not really reach there. The goal is to sort of take incremental steps towards that direction. And if things change along the way, then that's the process of diffusion. We can solve both of these problems fairly well. I will solve the first part, so I'll call this part 1, and I'll call this part 2. Part 2 is more mathematical, and part 1 is pretty straightforward after we have solved part 2. So let us solve part 2 first. So given xt and x0, how do we get xt minus 1? I'm just going to make a straightforward claim over here that if we know xt and x0, then we can express xt minus 1 as a linear combination of xt and x0 and some noise. So we can express xt minus 1 as a t times xt plus bt times x0 plus ct normal 0i. Right, so it's a linear combination of xt, x0, and some random noise. And this is a claim that I have for you. Don't worry, I will back up this claim very soon. But it shouldn't be very surprising, right? Given our current state and our final state, this is really saying our next state should be somewhere along this linear interpolation, right? Like, where else would it be? Like, you shouldn't be like somewhere else, right? Like, it will just contradict rotational symmetry, right? This shouldn't be surprising. And I want to just mention over here that AT, BT, CT are coefficients. Of course, they depend on T, but they are independent of states. So independent of xt or x0, right? They are just purely functions of T. And to derive this, we go back to our forward diffusion process. From the forward diffusion process, we should have seen this a lot of times, that it is just some multiplier times the previous time step plus some noise. And we can write it in the n step form, which is xt is equal to square root alpha t bar x0 plus square root 1 minus alpha t bar normal 0i. How does this help us? Well, the reason why we want to condition on x0 in the first place is because given x0, the probability density of all the random variables afterward in the process should be relatively straightforward. So the probability density that we want to find out over here is xt minus 1 given xt and x0, right? So this is precisely given our current state and our end state, how do we get the previous step? We can do a bit of Bayes rule over here because we really don't want this xt to be something that we condition on, right? We want to condition things such that the things that we condition on are the states that are earlier in the process. So this is equal to p. We want to swap these two terms. So this is equal to pxt given xt minus 1 x0 p xt minus 1 given x0 pxt given x0. But by the Markov property, right, pxt given xt minus 1 x0, this should be just equal to pxt given xt minus 1 pxt minus 1 given x0 over pxt given x0. And all of these over here, all of these probability densities over here are Gaussian probability densities. In the forward diffusion process, each of these are just linear recurrence relations. It is some multiplier times the previous state plus some random noise. So all of these three terms are Gaussian probability densities. And so we can just do the algebra and derive them out. But I also want to show another cool trick that can be applied to this problem. And this is really the niceness about exploring the intricacies of the diffusion process, because you can open up your toolbox and use a lot of things. In the diffusion process, we are injecting noise at each of those intermediate time steps. And all of those noise are independent normal random variables. So you can think about all the intermediate states as stemming from a source of t random Gaussians. And the framework that this sets up is really the jointly Gaussian random variables. So we can write that xt minus 1, xt, x0 is a jointly Gaussian random variable. And the nice thing about it is that this joint probability distribution is also a multivariate Gaussian, right? And we can write xt minus 1, xt, x0 as normal. We can assume all of its means are zero because we can scale the input. And let's say the covariance matrix can be written in this form: sigma 1, 1, sigma 1, 2, sigma 2, 1, sigma 2, 2, where this sigma 2, 2 is really the covariance matrix for the whole block xt, x0, right? You should think of this as a subblock. And what this essentially gets us is that we can apply the Schur's complement formula to get xt minus 1 given xt and x0 to be a normal distribution with exactly the parameters that we expect. And what does that mean? In this case, xt and x0 should have means of 0 and 0. If xt and x0 over-realize, that means if they are positive, then we should expect xt minus 1 to scale with respect to the covariance. And to put this in mathematical terms, it is really saying, given xt and x0, we should firstly normalize it with respect to the inverse of the covariance matrix, and we should multiply it by sigma 1, 2. And for the covariance, because we knew some values over here, the conditional variance of xt minus 1 should decrease. And by decrease, I mean that it should be less positive definite than sigma 1, 1. So it should be sigma 1, 1 minus some quantity. And this quantity is really, like, there's only one real form for it. It is sigma 1, 2, sigma 2, 2 inverse, sigma 2, 1, right? This will match the shape, and it doesn't really depend on the realized value of xt and x0. So I think the point here is that you can also just do the algebra on top and derive out that xt minus 1 is a Gaussian, but this is really a very clear-cut way to show that xt minus 1 conditional on xt and x0 is a Gaussian. We can just calculate out the sigmas really quickly. Like sigma 1, 2 is really the covariance of xt minus 1 and xt, covariance of xt minus 1 and x0. And what is the covariance of xt minus 1 and xt? If we look at the top, right, xt is a multiplier times xt minus 1, and the additional noise term doesn't really affect the covariance in any way since it's independent. So this is just precisely square root 1 minus beta t times the identity matrix, because that's the variance of xt minus 1, right? Remember the invariance. For the covariance of xt minus 1 to x0, we go back up and we look at the n-step equation, and we see that it should be square root alpha t minus 1i. For sigma 2, 2, we can do the same thing, right? This should be the covariance of xt with respect to itself, covariance of xt x0, covariance of xt x0, covariance of x0, x0. And this is equal to, well, the covariance of xt and xt should be I, right? Remember the invariance. So the covariance of a random variable with respect to itself is just the variance. So it is I. Similar for all the terms on the diagonal. The covariance of xt and x0, we can look back up at the n-step equation to know that this is square root alpha t bar I, square root alpha t bar I. And if we take the inverse of this, we can just apply the normal 2 by 2 inverse, which is 1 minus alpha t bar, switch the diagonal terms, do the negation of the off diagonal terms. And of course, sigma 1, 1 is just the covariance of xt minus 1 with respect to itself, which is just its variance and is equal to I. I think the upshot here is that xt minus 1 given xt x0 is just a Gaussian with the following parameter. So I'll spare you the calculation because I'm pretty sure everyone can do this computation. I just want to point out here that it is very straightforward to see why now I made the previous claim. Remember, the previous claim that I made was xt minus 1 conditional on xt and x0 is some linear combination of xt and x0 and some random noise. If you look at this matrix form, the mean is sigma 1, 2, sigma 2, 2 inverse times a vector of xt and x0. So it is already a linear combination, right? If you multiply xt and x0 by a matrix, that's a linear combination. So that explains the first half of this term. And then the variance, because all of these sigma 1, 1, sigma 1, 2, sigma 2, 2 have multiples of the identity matrix as their subblocks, the end result will still be some multiplier times the identity matrix, and that explains the latter term, right? And I just want to put here for completeness that AT is equal to just copying off the coefficients on top. BT is equal to square root alpha t bar beta t 1 minus alpha t bar, and CT is equal to, because this is the variance, we have to take the square root 1 minus alpha t minus 1 bar 1 minus alpha t bar beta t. And I'm pretty sure all of these are correct. You can work out the details. And just note that all of them have no dependence on the state. And that is exactly what we would want. Remember part 2 of the problem that I described above? We have already solved it, right? Given xt and x0, our prediction of the previous state will be precisely this expression here. So given xt and x0, our prediction for the previous state will be equal to atxt plus btx0 plus ct some random noise. Of course, like if we are trying to predict this, we wouldn't include the random noise. And also just for notation wise, this is coming from statistics. If I'm trying to predict a random variable, I'll put a hat on top of it to show that it is my prediction of it. It is not the actual xt minus 1. And now we want to return back to part 1. And what is part 1? Part 1 is really saying, given xt, how do we get x0, right? So we take some inspiration from the forward diffusion process. In the forward diffusion process, xt is equal to square root alpha t x0 plus square root 1 minus alpha t bar, some noise. We can give the noise a name. Let's suppose we call it epsilon t. So epsilon t is the cumulative noise from 0 to t. So we can write x0 as 1 over square root alpha t times xt minus square root 1 minus alpha t bar times the noise. And you might be slightly disappointed here because to predict x0, we would just use a neural network to predict this cumulative noise. And I just want to be very precise here. So when I say use neural network to predict the cumulative noise at time t, what I meant was firstly notation. So when I want to use neural network to approximate our function, I'm going to put the trainable parameters theta on top, right? Because that's exactly how we show that it is a model that is doing some prediction, and the theta is the trainable part of the model. What are the parameters that it takes in? Well, it needs to take in the current state xt, it needs to take in the current time t. This neural network epsilon theta t is something that takes a R32 by 32 image for our use case and a parameter t. So this t can be integers, or you can use some embedding of the integer. So let me just assume we embed it in some real space R, and it will give out the cumulative noise, which lives in the space of R32 by 32. And just to be very precise, what I'm saying is to predict x0 from xt, we would just use 1 over square root alpha t bar times xt minus square root 1 minus alpha t bar. We use the result from our neural network model, epsilon theta t xt t. And this is our prediction for x0. So we have solved part 1 of the problem using a neural network, and we have solved part 2 of the problem just now using some heavy math. Both are great. And so how do we combine these two together? Our algorithm for the backward diffusion process will be something like this. We are at xt, so we know the time t as well. So firstly, with our neural network, we can get our x0 hat, which is equal to square root that formula above. Then with this x0 hat, our prediction for x0, we use part 2 of our solution to get xt minus 1 hat to be atxt plus bt. You know, the reason why part 2 exists in the first place is because we don't have x0. But since we have already predicted x0 with our x0 hat, we're just going to use that here. In statistics, this is called using a plug-in estimator, because we are literally just plugging in our estimator for x0 into wherever it is used. So this is going to be x0 hat plus ct normal 0i. And because we have gotten a prediction for xt minus 1, we're just going to use that and continue the backward diffusion process. So we are almost done with the backward diffusion process, but I want to clear up some things. One question you may have is, since we are going to use a neural network anyway, why are we using it to predict the cumulative noise instead of some more direct things like x0 or xt minus 1, for example? And the reason is stability of the training, because this epsilon t, like regardless of xt or xt minus 1 or x0, in the forward diffusion process, it is always going to be a normal 0i random noise. Whereas if we do some prediction on xt minus 1 and xt, the distribution of it is going to be very dependent on what we condition on, in particular this xt or our current state. And to make the neural network training more stable, it is always better to predict something that is in a consistent distribution. And another thing that I want to point out over here is, you may be asking, why am I adding this ct normal 0i? Otherwise, the backward diffusion process will be a deterministic one. We want the neural network to get different states at different point in time to increase its generalizability. And that's why we add the noise. It also goes back to the life philosophy example where even if you know the next step to take, it's still good to have some variability in the things that you do so that you may get new inspirations that may lead you to a pretty different version of yourself in 5 years than what you have originally planned, which could sometimes be very good. And so this completes the diffusion model process. So let me bring back the diagram that I have from before. So we have investigated the forward diffusion process in detail, and now we have also looked at the backward diffusion process in detail. And our backward diffusion process is really reconstructing the image. So I guess the key equation here is we can get the previous step by a linear combination of a current state and prediction of x0 with some random noise. And this concludes the diffusion model process. Yay. But we're not done over here, unfortunately, because right, there is still a massive part that we have not covered, which is the objective, right? Since we have a neural network now, we need to discuss like what is a proper objective to train the neural network model. Otherwise, if we don't have an objective, we cannot backpropagate the gradient and we can't ensure that the neural network learns the right thing. This moves on to optimization. I think it is pretty useful to recap the problem. So again, our problem is that we have a data set of images x1, x2, all the way to xn. We want to learn a distribution. We have discussed the diffusion model as a model that maps a probability distribution to a probability distribution. And it has a neural network inside that is parameterized by theta. What is a suitable objective to train this neural network? Well, if we want to learn a distribution over this data set, the classical objective to use is the maximum log likelihood objective. Basically, if we have a model and a data set, we want to maximize the probability of us even seeing the data in the data set, right? That seems like a very good metric to optimize the model with. If the model doesn't even assign high probability to what we have in the data set, then who knows what it can generalize, right? Maximum log likelihood is essentially the sum of the log likelihood, so log of p theta xi, where p theta is the probability density implied by the model. And hence, we want to find the optimal set of parameters for the model. Theta star is argmax across all parameters, the log likelihood. So ideally, this would already work. We can just take this log likelihood objective, we take the gradient of it, and then we just backpropagate. But the issue is that in a diffusion model, there are a lot of intermediate states, and all of these intermediate states are latent variables. And this makes calculating the log probability very difficult. Why is that so? Because you should just imagine in a backward pass, right? We start with xt or the noise. We get xt minus 1 all the way to x1 and x0. All of these are latent variables. So to get log, let's say p theta xi, where this xi, right, is really this x0 over here, we need to integrate over the joint density, right? This is the marginal density of seeing the data. But to get the marginal density, we need to integrate out all the latent variables. So this is the log integral of the joint density. So xi, x1, dot, 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 xt, dx1, dx2, dot, 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 dxt, and this is really over the space of R32 by 32 to the power of t times, right? And this is a crazy integral. It's not something that can be easily calculated. Another but never say never, right? Because we are at a point where so many mathematicians have done a lot of the hard work before us, so we should use some of their results. We can try another way to look at the log probability. So the log likelihood is equal to, well, we have just said that we have to integrate out the latents. And let me just denote by z as the latent variable, because that is classically the symbol used to denote latent variables. And I'll let z be x1 to t, okay? The log likelihood, as we have said, we need to integrate out all the latent variables. So it's the integral of z p theta xi z dz. And now I think it really makes sense to understand why the variables are called latent variables. So the variables are called latent variables because they are unobserved, right? The only things we observe are those in our data set, which are the real world images. That's the x0 in our diffusion setup. But all the other variables, such as x1 to xt, are latent variables because we can't actually observe them. We only know how to generate them if we have x0, right? Given x0, we can inject noise to get x1 all the way to xt. So it makes sense to consider the probability distribution implied by this forward diffusion process, right? So let me just write it down. Consider the probability distribution implied out by the forward diffusion process, right? We understand the forward diffusion process very well, right? Each of the latent variables is just a multiplier times the previous latent variable plus some random noise. The forward diffusion process implies out a probability distribution, and we can write it something like qz given xi, right? Given xi, we can just inject noise, get the joint probability density of all the latent variables, and that is going to be q. And this helps us a bit in tackling this integral in the middle, because right now this integral in the middle is a joint probability density over both the latent and the observed variable. But it is really nice to write it out in q, because q is something that we understand. So we can write the integral as integral over the space of latent variables z. Let's just bring out q z given xi, and I'll divide by the same thing. We'll see why we bring out this term later. And the top remains the same, which is the joint probability density. This integral now resembles something that is an expectation of z over the forward diffusion process probability density, right? We can write it as log of the expectation of z sampling the latent from the forward diffusion process, which is q condition on xi, the expectation of p theta xi z qzxi. Well, how does this help us? The ultimate goal of doing all these calculations is that we want to simplify the objective such that if we apply the gradient on the objective, we should get out something that we can easily approximate by Monte Carlo or stochastic gradient descent. And right now, in this form, the expectation is inside the logarithm, which is very hard for the purposes of Monte Carlo or stochastic gradient descent. We would want the expectation to be outside of the logarithm. To swap expectation and logarithm, there is just one simple trick, which is the Jensen's inequality, right? So logarithm is a concave function, and we can just, for simplicity, assume a binary probability distribution, right? If you calculate the logarithm of the expectation, you get a point along the curve, which is like somewhere here. But if you calculate the expectation of the logarithm, you get a point on the affine interpolation of the two particular points, which is somewhere over here. So this is just saying that the logarithm of the expectation is greater than the expectation of the logarithm. So this is a greater or equal to, and this is really by Jensen's inequality, the expectation of log p theta xi z divided by qzxi, and the expectation is over the forward diffusion process. And this is already in a very nice state, right? Because now if we take the derivative of the objective, on one hand, we have the objective that we actually want to take the derivative of, but this is very hard to approximate by stochastic gradient descent or Monte Carlo. On the other hand, we have another objective, and this is really what we call the evidence lower bound. So in statistics, evidence is really the log likelihood of seeing the data, which is precisely this term over here, right? This is the actual objective that we want to maximize. But because most of the time it is very difficult, we maximize what we call as the evidence lower bound. And it is indeed a lower bound by Jensen's inequality. We lower bound it by assuming a particular distribution of the latent variable. So note that this Q can actually be any distribution, right? It is a variational distribution. For our purposes, we use it as the distribution implied out by the forward diffusion process, but it can actually be any distribution. And this Jensen's inequality will always hold. And this objective is something that's easy to optimize, because if we take the gradient with respect to theta, what we get is that the variational distribution, which is the distribution implied by the forward diffusion process in our case, is just used for sampling, right? This derivative can pass straight through into the expectation, because expectation is just an integral. And we know that this logarithm of the numerator over denominator is just logarithm of numerator minus logarithm of the denominator, and only the numerator is dependent on theta, right? The denominator, which is the variational distribution, is not even a function of theta, so it can just be eliminated. This will just be equal to the expectation of the gradient of log p theta xi z. right? The denominator doesn't even matter because it is a function independent of theta. And we see that the variational distribution here, which as I've said is equal to the probability distribution implied by the forward diffusion process, is only used for sampling purposes. It is not used in the objective at all. It is used just to sample out the latent variables, which are precisely the intermediate states of the diffusion model. Since we have worked out all these details, I would just want to complete the picture by saying to train, first we sample out a particular data point xi from the dataset D. We sample x1 to t using the Python notation by running the forward diffusion process. Right, in the forward diffusion process, this is actually our x0, and we just inject noise to get out our x1 to xt. This is essentially sampling from q given xi, right? Q is the probability distribution implied out by the forward diffusion process. And then from the variables that we have, both the observed x0 and our latent variables, we calculate our objective, which is the evidence lower bound, which is the gradient of log p theta xi z. Do backpropagation and stochastic gradient descent. And then finally, we repeat this process just to train our neural network. This all looks very straightforward except for the third step where we need to calculate out the gradient of the log of the joint probability density. So let me just fix up my notes because this z over here is really supposed to be x1 to t, right? Because this z over here is actually the latent variables, which is x1 to t. So how do we calculate this part? Now, for completeness, I will write how to calculate. This should be the term that we get when we run our backward diffusion process because we really need to calculate out the likelihood of seeing the data, which is x0, at the end of the backward diffusion process, given all these intermediate variables. And this is really just using our knowledge of the backward diffusion process. So the log of the joint probability density is equal to, if we decompose the backward diffusion process, right? So remember our backward diffusion process, we start out from xt to xt minus 1 all the way to x0. We can decompose it into p theta of xt times from t equal to 1 to t p theta xt minus 1 given xt. And this is really equal to the log of p theta xt plus the sum of the logarithm of the probability density of each intermediate step in the backward diffusion process. So I just want to note over here that the first term actually doesn't depend on theta. Because the model is only used for each of these intermediate steps between two states, right? The model is only used when we want to get the previous state from our current state. But at xt, we are not using the model at all. So this first term actually doesn't depend on theta. We can safely ignore it because when we take the gradient later on, it will just vanish. These terms over here is really the probability density of intermediate state transitions. So over here, we really want to leverage our knowledge of the backward diffusion process, which is that xt minus 1, we can write it as a linear combination of xt, x0 hat, and some random noise. And this x0 hat is really 1 over square root alpha t xt minus square root 1 minus alpha t bar epsilon theta hat xtt. So in particular, all of these are constant terms except for this zt over here, which is a normal 0i. So the probability density p theta xt minus 1 given xt is solely contributed by zt, which is a Gaussian random variable. So this should imply that the form of p theta xt minus 1 given xt should be a Gaussian probability density. So the log of p theta xt minus 1 given xt will be equal to minus 1 over 2 ct squared times the norm of the realized value xt minus 1 minus the mean, which is atxt plus btx0 hat squared. Over here, you just have to trust me a bit because I don't think the calculation will benefit anyone. But if you expand out xt minus 1 and xt in terms of x0 and the cumulative noise sigma t and sigma t minus 1, you'll be able to get that the inner term, you can extract out a constant, let's say c prime, and what is remaining in this norm square will be epsilon t minus epsilon t xt squared. Basically the MSE of the error term. If you look at what we are trying to do, we are trying to calculate the gradient of the log of the joint probability density. We have decomposed it into the sum of each individual stepwise log likelihood. And this is something that we want to maximize, right? Like we want to maximize this log joint density. So we want to maximize the summation of the log likelihood of each individual stepwise conditional probability density. And that reduces to minimizing, because of this negative sign, the MSE of the cumulative error term at each step. So loss is something that we want to minimize. So the loss can be just written as the sum of t equal to 1 to t, some constant ct prime prime times the MSE of epsilon t. And in practice, as what the authors of the diffusion model paper say, this CT is actually just set to 1 because it just empirically works very well. And we can write the loss as approximately just the sum of the MSE of the cumulative noise term at each individual step. Whew. So just as a recap, just now I mentioned to train, we first have to sample a data point from our data set, a clean image. We sample the latent variables by running the forward diffusion process, and then using the observed variable, which is our clean image, and all the latent variables, we calculate this gradient. And precisely what I meant was we should calculate and now we're able to fill in this step explicitly, right? Like we calculate the sum of epsilon t minus epsilon theta t xt t squared. We can get all of this because in our forward diffusion process, we should have already generated all of these epsilon t's, and we just have to get our neural network to match that. And then we do backpropagation, stochastic gradient descent, and repeat. I just want to say in practice, people write these laws as the expectation of first we sample with respect to t. We sample a data point x naught, and then we generate x1 to t via the forward diffusion process. And we just do backpropagation on that time step. So just epsilon t minus epsilon t theta xt t, where this t is what we have uniformly sampled over here. This is just a MSE on the cumulative error, and we don't have to do any summation over here. There's still some very interesting stuff that I want to say about the training though, so I'll just say it over here. Do you remember that we have used Jensen's inequality at some point? Remember we used Jensen's inequality. Precisely when we are trying to break down this log likelihood, we applied Jensen's inequality to get the evidence lower bound. The log of p theta xi is greater or equal to Jensen evidence lower bound. So evidence lower bound, we sample the latent variable with respect to a variational distribution. It may be conditional on xi or it may not. It doesn't really matter. Log of the joint distribution over the variational distribution. So this is our Jensen's inequality. But the use of Jensen's inequality over here actually masks a very beautiful fact, which is the difference between the actual log likelihood and the actual evidence lower bound is actually the KL divergence of the variational distribution with respect to the posterior distribution. I think there's a lot of English that I've said, so I'm just going to write it down in math. The difference between the actual log likelihood and the evidence lower bound, we can bring the actual log likelihood into the expectation because it is not dependent on z at all, which is the variable that we are integrating. So this can be written as log of p theta xi qz given xi over p theta xi z, which is equal to the expectation of z. You know, we can write the joint distribution below in terms of conditional distribution. So the numerator stays the same, and the denominator becomes a p theta of z given xi, p theta xi. And this is equal to the expectation, again, over z of log q z, the variational distribution, over p theta z given xi. And by the definition of KL divergence, this is really the KL divergence of Q, the variational distribution, with respect to P theta, the actual posterior distribution. Like, I think the point here is it would be nice if Q, the variational distribution that we use, is the actual posterior distribution. But obviously, that would be too hard to hope for, right? Like, if we know the posterior distribution, we wouldn't be using all these approximations anyways. But this is really to highlight that the gap between the actual log likelihood and the evidence lower bound is really just the KL divergence. Over here, we use the forward diffusion process as the variational distribution because it is convenient. We understand the forward diffusion process really well. And if we use that, we can get a very nice form of the evidence lower form, which just decomposes into the MSE of the cumulative noise. Another thing that I want to mention is really with respect to this evidence lower bound. We remember that the evidence lower bound is equal to over the variational distribution, the log of the joint density over the variational distribution, right? This is the evidence lower bound. Because we are very eager to take the gradient with respect to theta, we realize we can just ignore the denominator completely. But that again misses a very nice mathematical insight. Like, if we actually expand out this term, so recall that z, our latent variable, is actually the intermediate states x1 to t, right? If we actually expand out both the numerators and the denominators, so I'll write x1 to t instead of z just for clarity, right? So for the numerator and the denominator, we can decompose them into their respective step, right? So the numerator is really a backward diffusion process. We need to break it down starting from the back, right? So this is equal to p theta xt times the product of p theta xt minus 1 given xt. And the denominator, because for the variational distribution, we use the probability distribution implied by the forward diffusion process. So we can actually start off from the front, which is easier, right? It is equal to the product of q xt given xt minus 1. And we can just write this out as the expectation log p theta xt plus the summation of p theta xt minus 1 given xt minus the summation of... So over here, because I'm trying to bring out the mathematical insight, I want to convert the Q right now is xt given the previous state xt minus 1, but I want to convert it into the form of xt minus 1 given xt, and I can do that via the base rule. I also want to bring the term x0 because we would like to condition on a state that everyone knows. So in particular, I think we make the observation here that the probability density of xt given xt minus 1 is really the same as the probability density of xt given xt minus 1 and x0, right? By Markov property, it doesn't really matter if we condition on x0 or not over here. Xt in the forward diffusion process just depends on xt minus 1. So over here, we can write it as the log of, by applying base rule to this term, which is conditional on xt minus 1 and x0, we would get xt minus 1 given xt, x0, q xt given x0, q xt minus 1 given x0. So I just want to say over here that we can only actually start at 2 because we actually can't condition on x0, right? Like when t is equal to 1, the denominator is q of x0 conditional on x0, which is going to be like a delta distribution. So let's not do that. Instead, we will just handle the case where t equal to 1 separately. So when t is equal to 1, we still have our log q x1 given x0. So let me just write it out again. Log p theta xt plus the second set of terms, I'll keep it as it is. The third set of terms, I'll break it up. We'll get log q xt minus 1 given xt x0. And then I'll keep the other numerator and denominator paired together. And then I will subtract log q x1 given x0. And this is really equal to... Okay, now it is time to make some insights, right? So one thing we can note over here is This is a telescoping sum. Oh, sorry, didn't copy the logs over. So there's a log over here, and this is a telescoping sum because the log of numerator over denominator, where the numerator and denominator are index 1 apart, will just cancel out with itself. And also, this should be of an index 2, right? So what we will get over here is only the last numerator and the first denominator will remain. So we get something like minus log qxt given x0, where the t is the capital T, plus q of x1 given x0. But that precisely cancels off with these terms, right? So these two terms become just minus log qxt given x0. We also see that there is the summation of log p theta xt minus 1 given xt, right? That's the backward diffusion process, the probability of getting the previous state given our current state. And we also see that there is a subtraction of the log of the q xt minus 1 given xt and x0. So that's the probability distribution implied out by the forward process, right? The previous state given the next state and the starting state. We can write that as a KL divergence. So let us just combine it together first, right? It is the summation of t equal to 2 to t log of p theta xt minus 1 given xt over q of xt minus 1 given xt x0. Note that we have t equal to 1 remaining in the first term. That can be just left on its own, so there's a plus log of p theta x0 given x1. And then we have this lone term at the start, which is plus log p theta xt. These two terms can actually be grouped together because they look fairly similar. And sorry, just to write it better, in the end, we have three set of terms, right? The expectation of log of p theta x0 given x1. So that is this term right here. And the second set of terms has more insight, which is that it can be written as the negative of KL divergence, right? It can be written as the negative of the summation of t equal to 2 to t, the KL divergence of the distribution implied by the forward diffusion process of that particular step, which is q xt minus 1 given xt and x0 with respect to p theta, which is the actual backward probability distribution for that step, p theta xt minus 1 xt. And these two terms is also a kind of a KL divergence. It is the negative of the KL divergence of qxt given x0 with respect to p theta xt. We have went through a lot of trouble just to get this insight. I think the upshot over here is that the elbow can be decomposed as the summation of KL divergences of the respective consecutive steps in the forward and backward diffusion process. Both processes imply out the probability distribution of the previous state given the next state. And the elbow is really just summing up the KL divergence. Well, it is the summation of the negative KL divergence because elbow is something that we want to maximize. KL divergence is a measure of distance between two distributions, and that is something we want to minimize, right? So by maximizing elbow, you're trying to minimize the KL divergence. You're trying to minimize the disagreement in the distributions implied by the forward and the backward diffusion process. And that is all I want to say for the optimization objectives.